Greetings. Now we are into the topic of integration. So integration is the reverse of differentiation. So when you have a function that you differentiate, you can integrate and get back the formula. And when you do this, sometimes the constant is lost after you differentiate, and when you integrate, you don't know what the constant will be, so you usually add an arbitrary constant for the value that you want to find, and you can determine the formula so long as you have gradient function and coordinates. And the integration is a linear type, since is the same when you add and subtract, and the constant can be put out of the integration formula. And when you want to find out how all the integrated expression yields the following, you can just go back to differentiation, and then when you integrate, eventually you see how it works. Just make sure that integration is the reverse of differentiation. Let's look into definite integral. Unlike indefinite integral, this integral will give you the net output that is defined by two input limits. This can be represented by a net area under graph by integrating the original function. Now, indefinite integral has more rules since it accounts for the use of limits. For the first one, there is no net area, thus the output of integral is 0. For the second case, because the limits are swapped, eventually you can unswap them and you just add a negative value behind it. For the third case, it's the same as the indefinite integral, and you can just prove it by using the original definition shown at the top of the picture. For the fourth one, sometimes the integral can merge due to them having the limits of the same value. As such, if B is the intermediate, eventually you can combine them. You get C as the upper limit, A is the lower limit. And as for the fifth one, it's the same as the indefinite integral. Let's look at area under graph. As explained earlier, a definite integral will give us the net area, and to get the proof, you can see at the top the sum of area plus the limits, and you work it out. Eventually you get the formula for area under graph, and you show that this is definite integral as explained earlier. This is used in analysis such as kinematics and thermodynamics. Now, when you want to find area under graph, make sure you draw the graph and split the area into parts, as sometimes area at different sides of the axis will have a negative value of the area. So to counter that, you just draw the graphs, split the area, and find out how to calculate the area of each component separately. Now, let's look into volume of revolution. Now, just like how you find the proof for area, this time you do it for volume of revolution. And all you need to do is you just think of an analogy like this. You put the cylinder discs of different sizes, and then you stack them up, and then when you sum the volume, make sure the limit for delta x approaches 0. Eventually you get the estimated volume to be nearly identical to the actual volume, and you get something such that the volume generated is revolved around the x-axis. This is used in architecture and engineering. And as for volume of revolution, the reason why pi is here is because we're using the cylinder formula. And if you want to to do volume revolution involving two functions, make sure that the outer volume is subtracted by the inner volume. That's how you get the volume revolution that involves two functions. Now we are looking into integration by parts. Integration by parts is useful to integrate the product of functions, and to get the by parts formula, integrate the product rule that was found in differentiation and then you rearrange the formula. That is how you get the formula for by parts. And when you want to integrate by parts, you need to choose a function for u and dv. And to do this, you need to follow the Eilert guideline when you choose u, and this is to ensure that the u is reduced to a constant variable. And this also makes sure that your working will not be an infinite loop. There's a case where if you have an exponential function multiplied by an original trigonometric function, then you eventually get a deadlock where you'll be stuck in a loop. But don't worry, because e to the x integrated to get e to the x, and sinusoid functions will repeat. Eventually all you need to do is pop trigonometric function as u, and then you take dv as e to the x, and you integrate by parts twice. Eventually you get a constant that can be separated out from the integration, and then you get a definite value. And when you do by parts for definite integral, make sure the part uv is also included when involving limits. And for what I believe why most students cannot do this is because they forgot to put the part uv when you integrate by parts. Let's look at the possible integration techniques that you use. Okay, so on the left picture, top there is partial fractions. So you need to use all of these techniques that I taught in algebra in the previous video, and then you can see why partial fractions is important in here now. And if you look at the bottom there, you have substitution. So substitution works something like this. You take an expression and then make it equivalent to that variable as a subject. Then you substitute the one variable for another, and then you perform integration that's much simpler than the original. And when you do indefinite integral, don't forget to change back to the original function. The one on the right is involving trigonometric identities, and this also shows you how to perform integration by parts. And it also involves the use of logarithmic differentiation, in which I've already covered in the previous video. So you can also see how the integration to reverse the logarithmic differentiation, that is how you get your final answer after you finish. Now let us look into a special case where you have both an exponential function and a sinusoid trigonometric function. This is a deadlock situation where neither function can be reduced to a constant. So all you need to do is take u, and then make sure you choose the trig function, so that when you differentiate, it's easier to convert. And as for exponential, when you integrate, you just be the same function, thus doing it is much easier that way. And if you do this twice, eventually you end up with a result such that 2 is the constant, and when divided you get a complete constant with the plus c. That is how you do integration by parts if there's a loop. And also, when you want to do definite integral, make sure you include the part uv, as most students, I believe, or forgot to include this simply because there's no integral when you use the formula. Unfortunately, that will give the wrong value. So make sure you include uv, the term, when you perform definite integral. Now, let's look at differential equations, the last subtopic for integration. So, this is how differential equations will look like at the top right, and that is how you separate the terms, and then you integrate separately. For these differential equations, we focus on first order and separable terms. So for the steps, first formulate the equation according to the question given. If there are variations like the rate is directly proportional to let's just say a number of units, then you form the variation first before you formulate the complete formula. If there's a rate decrease, make sure you add a negative sign. Then separate the two terms so that each terms are integrated separately, and integrate on both sides. Complete the formula with the given information, and even if there's a constant, just make sure that the constant only stays on one side. And I'll use the radioactive decay formula as an example. Look at how it's formulated. Since the decreasing activity is directly proportional to the number of particles present, eventually you arrange the constant used is the decay constant lambda. Integration occurs since it's definite. That's why you have the values at the upper limit and the lower limit, and it's different for different variables. After that, you arrange and then you complete the formula. The applications for differential equations include chemistry rate law and radioactive decay, like as shown on the bottom right. And I believe that is all for my video. I hope you all learn a lot in this chapter. Thank you.